In this lecture, we'll talk about more general control gates. And we'll also start talking about universal quantum computing. So thinking about the minimal sets of gates that are needed to implement any unitary operation on a system of n qubits. So last time we talked about a control gate where you have one qubit controlling another qubit. So if the first qubit is 1, a single qubit unitary acts on the second one, and if the first qubit is 0, nothing happens to the second qubit. Essentially, there's an identity that acts on it. And we managed to decompose that in terms of just the C0 and a bunch of single qubit gates without control. So we mentioned that, so let's just go back briefly to the previous lecture. We came up with this particular decomposition of this more general, but essentially 2 qubit, one qubit controlling another qubit control gate. So then we ended last lecture by noting that in general we can have more qubits controlling a certain number of qubits. So what I want to do now is to think about still the qubit being controlled. Let's say there's just one qubit, but we want to have more qubits controlling it. So we want to apply, let's say, a unitary U on some qubit if and only if a whole bunch of other qubits are 1. So this is an example, maybe with 4 other qubits being equal to 1. In general, let's say we have here, we have n qubits that control this one qubit. So this operation, if you have any base state that's like 1, 1, 1, 1, and then something else here, should take it to 1, 1, 1, 1 tensor U times that sigma state, which can be 1 or 0. And otherwise, so any other state where these are not 1, 1, 1, 1, if any of them is 0, it acts as identity. So in order to construct this, we're going to start by the n equal 2 case. So for n equal 2, we will develop some decomposition of this circuit here. So I have 2 qubits that control a third qubit. And then this unitary operator U acts if and only if these 2 are 1. So the way to do this is to come up with some decomposition of U. So let's do this. So suppose I can write the unitary U as some unitary squared. So let's say U is V squared. There's there's some other unitary that when you multiply that by itself, or when you act twice, you generate the unitary operator. So I'll discuss a bit later how we can determine U if you're given some 2 by 2 unitary U, how we can find a 2 by 2 unitary V such that V squared is equal to U. But suppose we have that and we are able to implement this. So let's leave like an example of just deriving this for later. But then I'll just write the answer, and we'll try to make sense of it. So essentially the idea is, if V squared is U, then we can have, like, suppose we put somehow 3 operators that are somehow controlled by single control operations. And then let's say the first one is V, the second one is V dagger, the last one is V again. So if I engineer my controls in a way that, you know, for some sets of states for the control bits, the first 2 ones, V and V act, then U is the operator that acts on the third qubit. And if I engineer all the other cases such that one of the V's doesn't act, so I either get like V dagger or I get V dagger V, then in those cases we know that V dagger is the same as V dagger V is equal to the identity. So V is also a unitary. So I want to like play with how these operations are controlled in such a way that I guarantee that when the first 2 qubits are 1, I have 2 of the V's acting, so I get a U, and in all other cases, there are 3 other cases, like they could be 0, 1, 1, 0, or 0, 0. In those other cases, I either want like nothing to act, so I just get an identity, or if something acts, I want it to be a V and a V dagger. I want one of the V's not to act. So we can think about this, and the solution is as follows. So let's say the first one is just controlled by the second qubit. Then I put a C0 here. So the first one, if it's 1, it flips the second qubit. And then now this V dagger is again controlled by the second qubit. I put another C0. And a C0 flips if I have a 1 here. And finally, I allow this one to control the last one. So by this construction, let's see what happens. So let's consider, let's say the 1-1 sigma case, right? Where we want 2 V's to act, so that we get our U operator. So in the case of 1-1, well, first the V acts, because this is 1, so that control operation works. Now, when this C0 gets applied, I have 1-0 for the first 1, because this C0 is flipping the second qubit. So now, because this guy is 0 now, this V dagger doesn't act. And then I keep going, and then I flip back that 0. So the effect of these 2 C0s, when you place them around here, is that when the second qubit is 1 and the first qubit is 1, it makes this V naught not act because it turns the second qubit to 0. And then this control means that this operator, this V dagger, acts as identity. So I go back here, again, there's another C naught, so this now turns back to 1. So again, at this point here, I have my 1, 1. And then because the first one is 1, I have a second V acting. On my last qubit. So the 1, 1 again doesn't change as we went through this operation. The first one is never controlled, so it just remains 1. The second one, it turns into 0 and turns into 1 again. So it's going to remain 1. So this works, right? If I have the 1, 1 case, if both of the first two qubits are 1, then a V squared acts on the last one. So that's good. Let's now take the 1, 0 case. So I have 1, 0 sigma. I realize sigma looks a little bit like 0. So try to emphasize that here. So, so if I have the 1, 0 case, well, what happens? So you think about the last qubit, this V doesn't act, right? Because the second qubit is 0. So that's out. Then now the first one is 1. So at this point, when this C naught acts, this qubit becomes 0. It flips it. Because it's 0, then, sorry, this qubit becomes 1, right? It's initially 0. It gets flipped, it becomes 1. And now, because it's 1, this V dagger does act. So now the 1 goes back to 0 here, gets flipped again by this C naught. This guy is 1, so the C naught does flip this. And finally, this one is 1. The first qubit is 1, so this V does act. So I have a VV dagger acting on my last qubit, but VV dagger is the identity. That's what we wanted. So, and then the first one remains 1. The second one, it started with 0. It became 1 here. It became 0 here. So the C naughts flip it 0. So that works as well. If I have the 0, 1 sigma, so the last one is whatever it is. I'm considering the case of 0, 1. The first one is 0. So if the first one is 0, the C naughts don't act. And the last V doesn't act. So the first one is going to just remain 0. It's not controlled by anything. The second one, again, these C naughts don't act. They act as identity because the first one is 0. So the second one will remain 0, will remain 1. And what is the fate of the last one? Well, because the second qubit is 1, this V acts. And then again here, this V dagger also acts, right? The second qubit is 1. It wasn't flipped here, so I have a V dagger V. And again, that's equal to the identity, so that works. And finally, if you have 0, 0 sigma, well, the 0 just remains 0. And then nothing acts, right? So the C naughts, it's as if the C naughts are not there. Then the second qubit is 0. So these V and V dagger don't act. This final V doesn't act because the first one is 0. So by thinking about a unitary such that when you square it, you get U. And then putting a bunch of C naughts and controls in a way that when you have 1, 1, we get the 2 V's. We kind of engineer our circuit in a way that this V dagger doesn't act in that particular case. And in other cases, we either have like nothing acting, so in the 0, 0 case, or if for the 1, 0 and 0, 1, we either get a V dagger or a V dagger V, and both of them are equal to the identity. So, so this way we manage to essentially write a control gate where 2 qubits control 1 qubit, decompose it in terms of C naughts and gates where 1 qubit controls 1 qubit. And gates where 1 qubit controls 1 qubit, again, we had previously decomposed that in terms of C naught and single qubit gates. Okay, so now let's think about a more general case. Again, if I have this building block, have just by C naughts and single qubit gates, I've constructed a control gate where 2 qubits control the last qubit. Then if I have an arbitrary number of qubits controlling the last qubit, we can make use of now this building block where n is 2 to make more general control gates. So suppose now I have let's say 5 qubits. So next step, use n equal to control to make arbitrary n controls. Okay, so we want to control U, but instead of 2 qubits, we have a larger number of qubits. So one recipe that does it is quite simple. It makes use of a bunch of auxiliary or work qubits that I can initialize to be 0. And then essentially by repeated use of this 2 controlled gates or a 2 controlled flip operation, we can make sure that U only acts if all of them are 1. So the way to do it, let's do it for, so imagine I have maybe 5, 2, 3, as I have 4. So suppose I have qubit 1, qubit 2, 3, and 4. These 4 qubits want to control the last one. So I want to implement something like this. If all of these 4 are 1, if I'm in the 1, 1, 1, 1, then here I act with a U, and otherwise I act acts by an identity in the last qubit. So in order to do this, I have to introduce n-1 qubits here. So these are a bunch of work qubits. So these are control bits. These are the ones we care about. And then we make use of a number of other qubits. So let's call them work qubits. And we initialize them to be 0. So I want this U to act on this last qubit. This is the qubit being controlled. If and only if all Q1, Q2, Q3, Q4 are equal to 1. Okay. So one approach that I can take is this. So I can put a 2 control qubits. So this guy starts with 0, this first work qubit. So if I put a 2 qubits control gate here on the first 2, so if and only if the first 2 are 1, then I flip this guy here. So that's like a 2 control C naught, essentially, like so imagine this is the X operator that flips. So if and only if the first 2 are 1, this 0 becomes 1. Now I can put then another one of these on this one, on the third one, and this one. So now if and only if Q3 is 1 and this one is 1, and this one is 1 if and only if Q1 and Q2 are both 1. So I will have this operation acting here, this flip operation acting here, when Q1, Q2, and Q3 are all 1, right? Because Q1 and Q2 have to be 1, so this 0 becomes 1, right? And then now this has to be 1 and this has to be 1 in order for this to act. And then we can keep going. Now this is 1, this second one becomes 1, if and only if Q1, Q2, and Q3 are 0. So now if I do another control using Q4 and this guy here, then this flips the last one only when all these 4 are ones. So by kind of adding these work qubits, then I can make use of my 2 control to create a control that's 1, right? When all of these control qubits are 1, and then I just put a single qubit control gate over here. So this does the right thing for U. Sorry, for the last qubit. So the last qubit, if it's sigma, it goes to U times sigma, whether sigma is 0. But then, of course, I have to undo what I've done, because I want for all combinations of Q1, Q2, Q3, this thing should act as U on the last qubit if the first 4 qubits are all 1, otherwise acts as identity on the last one, but also it should not change these control qubits. So this, you see, it does it actually doesn't change the qubits we care about, right? So these are never controlled by anything, but it does change these zeros. So if you want to return like these to their initial state, so there will be some flips acting on them depending on various combinations on Q1, Q2, Q3, Q4. So I can always undo that by putting, in this order. I can just put back these operators. So if these 2 were 1, and then this got flipped, now again, these 2 are 1, and then this gets flipped back. So regardless of whether this is 0 or 1, these 2 these two cancel each other out. Again, I can cancel out the effect of this one now. And I can put now this one over here. So this full circuit not only doesn't change the control qubits we care about, it doesn't change the qubits we initialize to 0. So if you want to use them later, we can use them again. So they're not changed. We just undo what we did to the work qubits here. So you may be wondering why we constructed our control gates such that when the control bits are 1, some non-trivial unitary acts. And that's just a matter of convention. In fact, there are control gates that do the opposite. So let me do this. So this takes 1 sigma to 1 tensor u times sigma, right? Acts with a u on the second qubit, and takes 0 sigma to 0 tensor sigma. Doesn't change it at all. There are these other type of control qubits. So instead of a full circle, we put an empty circle like that. Instead of a dot, we put a circle, and we don't fill it, an open circle like that. So this does the opposite. So when the first qubit is 0, you act with a u on the second qubit. So this takes 1 sigma, goes to 1 sigma, doesn't change, but 0 sigma goes to 0 tensor u sigma. So it turns out this is really easy to construct in terms of this. So essentially the way to do this is we can say this is equal to, I just put an x here, flip this guy. So then if it was 0, now it becomes 1 after the application of that x, and then I put one of these standard controls, and then I put another x operator to flip it back. So if it was 1, it's 0 here, and then the u doesn't act, and then again it's turns back to 1 because I have 2 of these x's. So x squared is equal to the identity, essentially. You flip once and you flip back. So x squared never does anything, but in the middle there's been 1 flip, so it would do the opposite. So that's a simple construction, and it's an important notation to be aware of. All right, so there was something that I skipped over rather quickly. So I said that we can always find this matrix V for some 2 by 2 unitary U. We can always take somehow the square root of it in some sense. So I want to elaborate a little bit on that and just find a way of doing it in practice. If we have some unitary U, what is that unitary V? Such that when you square it, you get U. All right. So in general, a unitary U can be thought of as the exponential of a of I times the Hermitian matrix. So I'm introducing a whole bunch of jargon here. And I'm not going to prove things, but so essentially, we've talked about the exponential of a matrix and a Hermitian matrix. So let me put a title here. So we're talking about how to find V such that V squared is equal to U. All right, so we want to find this so-called square root of a unitary operator, U. So a Hermitian matrix has the property that H dagger is equal to H. So in general, for a 2D, if you want to write the most general Hermitian matrix, we would put like a real number A here, a real number B here. So this means that if you complex conjugate it and take the transpose, so in terms of components, this is H star Ij is Hji. So that means that the diagonal elements are going to be real because they must be their own complex conjugate. And then the only off diagonal we have for a 2 by 2 is 1, 2. So if I have C plus ID, here I must have its complex conjugate, which is C minus ID. So that's the most general 2 by 2 Hermitian matrix. And the unitary 2 by 2 unitary is the exponential of some of I times some Hermitian matrix. So now suppose we find the eigenvalues and eigenvectors of H. So the eigenvalues are going to be real for a Hermitian matrix. That's a theorem. So I'm not proving this at this point, but it's a general theorem. So let's write those eigenvalues. So suppose H times lambda 1, this is an eigenvector, is lambda 1 times lambda 1. This is the eigenvalue. And H times lambda 2 is lambda 2 times lambda 2. So then I can write H. So this is a column eigenvector. 2 by 2 matrix times a 2 by 1 column is some number times a 2 by 1 column. So it turns out I can write H as lambda 1 times this column matrix product with a row that essentially turns the column to a row and complex conjugates it if there are complex numbers in it, plus lambda 2. Okay, so let me give an example here. So suppose my H is just the X operator. It's 1, 1, 0, 0. We see it's Hermitian. It's both unitary and Hermitian in this case. So that's a Hermitian operator. The eigenvalues are going to be +1 and -1. The eigenvectors are 1 over square root 2, 1 over square root 2. And 1 over square root 2 minus 1 over square root 2. As you can see, X is an operator that flips. So flipping when the two elements are the same doesn't do anything. Flipping when the two elements differ by minus sign just changes the overall sign. So this decomposition of the matrix in terms of its eigenvalues and eigenvectors, I can just check it in this case. So if I construct the right-hand side of that equation, so λ1 this becomes 1, right? The row corresponding to this, they're real numbers, so I don't worry about, sorry, the column first, 1 over square root 2, 1 over square root 2. Then the row corresponding to this, 1 over square root 2, 1 over square root 2, plus -1, the second eigenvalue. Now this column. One thing I didn't mention is that these eigenvectors must be selected to be orthonormal. So by construction, if you have a Hermitian matrix and you find two eigenvectors with different eigenvalues, they're going to be orthogonal. As you can see, the inner product of this and that is 0. It's 1/2 minus 1/2. And then we've put those factors of square root 2 to make them normalized. So the inner product of each of them with itself is 1. Okay, so now if I construct this, so what do I see? So I have a 1 here, then you do that matrix multiplication, first row, first column, 1/2. So everything is going to be 1/2 here. Then you have minus first row, first column, 1/2. First row, second column is going to be minus 1/2. This is going to be minus 1/2. This is going to be 1/2. So the diagonal elements cancel out. The off diagonal elements add up. It's going to be 1/2 plus 1/2. So we have this 1, 1 matrix. So that's an expansion of this Hermitian matrix in terms of its eigenvalues and eigenvectors. And then now in this case, if you exponentiate, you see it's, if I look at e to the IHT, or e to the IH rather, so I'm going to Taylor expand this whole thing. But anytime so let's do it a little bit more slowly. So I'm going to get the identity plus I times, let's say, λ1 plus I over I squared over 2 factorial, this thing squared, etc. So then, as you do this, we'll see that when you square this, for example, I'm going to get terms that look like λ1 times λ1. Let's look at a term like that. right? So then because it's normalized, this is just an inner product of lambda 1 and lambda 1. This is 1. So any power of lambda 1, lambda 1, and lambda 2, lambda 2 is going to be the same as itself. So that means to any power is the same. Similarly for the other one. And if you look at some cross terms, so if I have lambda 1, lambda 1, then there's going to be some cross term when you square it, which is lambda 2, lambda 1, lambda 2, lambda 2. But then this is 0 because these are orthogonal. So that's 0. So the cross terms go away. So essentially, I'm going to be left with so I have an I here. Of I lambda 1 plus I squared over, let's say 2 factorial lambda 1 squared plus all of these. And then here we have lambda 1, lambda 1. And then the same thing for lambda 2, lambda 2. And this I can be written as lambda 1, lambda 1 plus lambda 2, lambda 2. So see, this acts as identity. So you essentially lambda 1 and lambda 2 provide like a basis. So any vector you can write as a linear combination of lambda 1, lambda 2, and then when this acts on it, the lambda 1, just picks the component that has a lambda 1 in it. So let me just do this here quickly. You act on, let's say, alpha lambda 1 plus beta lambda 2, which is some general 2 by 2 vector. Well, this guy acting on that is orthogonal. It gives me 0. Then lambda 1 times lambda 1 is 1. So it gives an alpha, and then what remains is lambda 1. And similarly for this. So then using this, we'll see that essentially this I can add a 1 to each of those expansions, and U ends up being e to the I lambda 1, lambda 1, lambda 1, plus e to the I lambda 2, lambda 2, lambda 2. So essentially, this is the diagonalized form of U. So lambda 1 and lambda 2 are the eigenvectors of U. And the eigenvalues of U are these phase factors. They're e to the I times some real number. So now in this notation, I can very easily construct a V. I can write my V. I write e to the I lambda 1 over 2. Then we see that V squared is equal to U. Again, there is orthogonality. So as you multiply, the cross terms go away. The terms that are not a cross term just give me 2 e to the I lambda 1 over 2 times e to the I lambda 1 over 2, which is e to the I lambda 1. And then 2 of these operators, again, lambda 1 gives me 1. So that's like a recipe for finding the v, if you're given a u, finding essentially the square root of this unitary. So this, we can maybe do an explicit example here. So we said X is an operator that both Hermitian and unitary. So essentially, we know how to find the eigenvalues and eigenvectors from our linear algebra courses. And for X, we already did that. So if I want to find the square root of X, right? So how do I do this? Well, so X we can write as 1, right? So finding, so X is unitary. Find V such that V squared is X. So this is a particular example of this. So X is going to be 1 times this vector times -1, let's say. Let me write it plus -1. So we said these guys are e to the I times some real number. And we can say, well, we can find those real numbers. So I can write 1 as e to the 0, I times 0, let's say. And -1 is going to be e to the I pi, right? So we look at the complex circle. So 0 is here. Its cosine is 1. Its sine is 0. So e to the I 0 is 1. For pi, the sine is 0. Cosine is -1. So e to the I pi is going to give me -1. And then this recipe tells me that v should be, you divide 0 by 2, you're going to get the same thing. So this seems to be the same. And for this, instead of -1, which is e to the I pi, I write e to the I pi over 2 times this. So we're saying v in this particular case, when u is x, is 1/2, 1/2, 1/2, 1/2. E to the I pi over 2 is going to be cosine of pi over 2 is 0. Sine of pi over 2 is I. So that's just I. 1/2. So the claim is that the V operator is something like this. It's going to be, factor out the 1/2. It's going to be 1 plus I, 1 minus I, 1 minus I, 1 plus I. So hopefully that works. Here's a moment of truth. So let's do V squared. I'm going to get a quarter from those two 1/2s. 1 plus I, 1 minus I, 1 minus I, 1 plus I. So first row, first column is going to be 1 plus I squared, which is I think it's 2I, right? It's 1 plus I squared is -1, so they go away. The cross term is just 2I. And then this is going to be this is going to be minus, right? It's again, this is going to be minus 2i, right? It's 1 minus I squared. So that seems to give me 0. That's fine. Then first row, second column, it's going to be 1 plus I times 1 minus I. So that gives me 2. Then plus 1 minus I times 1 plus I, that gives me 4. So that's good. Second row, first column, again, 1 minus I, 1 plus I is 1 minus I squared, which is then 1 plus 1, which is 2. Similarly for this, that's 4, 0. So yeah, so that works, right? So that's a recipe that any 2 by 2, we just need to find the eigenvectors and eigenvalues, make sure we write the eigenvalues as e to the I times some real number. And we make sure the eigenvectors are orthonormal, they're normalized and they're orthogonal to each other. Again, if the eigenvalues are different, they should be automatically orthogonal. And then we can construct this V. So going back to our recipe for decomposing the U, so U is some operator, some single qubit operator that's given to us. We can always calculate this V such that V squared is U, and then we will know, and then V dagger is again, it's conjugate. So these are some single qubit operators that we can construct. So we have these single qubit operators. Again, we have to make a decomposition of this to write this in terms of C naught and just single qubit gates without any control. But all of this reduces once we find the V.